Um, Arhan, thank you very much. Hello, everybody. Good morning. Thank you for staying the course, literally. um, Not just my course, but Maribel's as well. It's been the end of a week. I think we're all a little tired, so I'll try to take it slightly easy today and still cover the material. Concerning material, as I said in the first lecture, I don't know how long this will take to present. It's the first time I've done this. So I've tried to, I think it's worse to run out of time than to have time left at the end. So don't be embarrassed if I finish, run out of material early. If I do, that's fine. But also feel free to ask questions. Your questions are more valuable, actually, than me talking. In fact, hands up if you think that anything you have to say is going to be more valuable for your understanding than listening to me natter on. Hands up, please. Sorry, I misphrased that. Yeah, come on, everyone put up your hands. Go for it. That's more like it. Okay, so, you know, questions are good. Questions are better than good. They're excellent. So we are now on the start of lecture 3. I have loaded up GHCI and I will get my re-environment set up. Okay, so that's me loaded up some. Here we are. I will create my names. I was thinking about this lecture yesterday. Oh, yeah, sorry I couldn't participate in the Slack channels yesterday. As basically, I've been on the go since my last lecture ended. I just didn't have time to sit down and work through all the comments. I will endeavour to do so. Do feel free to follow up with me. If this is something you really want to ask and I haven't addressed it, then just ping me again, okay? That's life. Fahad, could you confirm that that's the correct procedure? If somebody doesn't answer you the first time, you don't retreat into hurt feelings, you just ping them again. Would you agree with that? Yeah, thank you, Ahad. That's a wisdom that I didn't have when I was 20. If somebody didn't answer it, I just felt like they were ignoring me. They weren't. They just were busy with other stuff. Okay. I might have to import data set, but okay, I'll do it now. What the hell? So import data set as S. So now I have s.fromList, for example, if I want to make a set. Let's try that. Cool. Okay, so A, B, C. Hands up if you're okay with everything I've done so far, please. Cool. Thank you for that. Now, did I mention support? I guess not. Okay, so I touched on Unify. Yes, that's right. I touched on Unify Perm. That's where we ended up last. So let's talk about support. So let's look at some supports. Hands up if you're familiar with the notion of support from nominal sets, so the mathematical definition. Okay, hands down. Hands up if you're not familiar with the mathematical notion of support. Goodness gracious me, such wasted lives. Okay, so it's a symmetry property. The support of an element is the finite set of atoms such that if you fix those atoms pointwise, the element won't change. So, for example, if we look at lambda x equals a, this is a function. It's perfectly well typed. Mathematically, the type of this thing is singleton A, right? Because if we apply a permutation to this function, can you see my point? Yes, you can. If we apply a permutation, permuting a for b to this function, then it will change to lambda x equals b. But if we fix a and apply a permutation, then nothing will happen. Hands up if that makes sense, please. Good, good. If you have a question, put your hand up now, because otherwise I'll just move on. Thank you. So that's a mathematical notion of support, and I chose this example of a function deliberately because it's significant that nominal techniques have a notion of support that interacts well with functions and power sets. For me, this is why it feels mathematical. This support is not it's not an inductive, it's not defined by induction on your data. Support and permutations are two things that just come from the nominal universe for free. And that can be very significant. However, functions are not an equality type, so the Haskell notion of support that's built, let's just look it up, IK-sup port. This thing here, this thing is defined just for a few types, but not for functions. So what's the support of the list AB? Well, it's just the set AB, and the support of MA/MB is just, again, AB. Now, did I build complex names? I don't think I did. So let me build a complex name. NNA is going to be equal to name, and I'm going to label A with B. Let's see if that works. Haha! Okay, so let's look at NNA. So this is A with a B label. So it's a name that's labeled with a Tom, and it's identified by an atom. What could be confusing about that? Let's just check what the support of NNA is. There you are, 1, 2. So we can see what support is doing. Support is just going down. It's a wee machine that goes down through the structure of a data type, and it just picks out the atoms. SUP, importantly, SUP knows what to do with abstractions. You see there, the support of the pair MAMB is just AB, and then this abstraction has removed the atom in MA from the support of this thing. Hands up if that makes sense, please. Cool. It's not a complicated program. It's just another one of these generic boilerplate machines that Haskell lets you write. It's completely type directed. We tell it what to do at each type. So somewhere in the system, there's a little machine that tells support that in order to calculate the support of an abstraction, you calculate the support of a body, and then you subtract the abstracted atom. And it really shouldn't be a surprise that we get the same behavior from restriction. Yeah. Who thinks the support of this should be just B? Hands up, please. Okay, down, please. Who doesn't know what the support of this thing should be? Interesting. Okay, James, could you please unmute your microphone and tell me what's not clear about this, please?
Oh, that one. That's a fair question. I guess I didn't quite understand from last time the difference between restriction and abstraction. I just think it might do something strange.
That's a fair point. So James has said with courage and honesty that he doesn't understand the difference between restriction and abstraction, which is entirely fair. It's quite subtle. But I hope you'll agree, James, one thing that restriction is going to do is restrict atoms. So it's going to remove atoms from the support. It's a binder. Would you agree with that, James?
Yeah, that was my guess anyway.
Yeah, it sounds plausible. So you've touched on a general point here, which I'm going to come to very shortly, there are actually many binders. There are many possible binding operators. I've shown you just two, abstraction and restriction. There are many more. But what they all have in common is that they bind atoms. So in a sense, this is it. This is where, in one sense, this is where all the action is going. What res does is it binds the names A and C in the body. And abstraction abstracts them. The difference between restriction and abstraction is that abstraction is a pointed operation. When you abstract MA here, we still remember, we forget the name, the atomic identifier of MA, but we still remember that MA is restricted, is bound here. So abstraction it's a bit like a pointed set, right? Whereas here with restriction, we abstract A and we're supposed to forget the order and the identity of everything in this list. So that's why I put in the C here. We restrict C in MAMB. Here, I'll just show you something. Maybe this will help. So just get a load of that and get a load of that. Notice that these two things have the same type. Agreed? James, could you put your hand up if you're, in fact, everybody, can we agree that these are the same type? Yeah, thank you. So if we restrict by one atom, it's the same as restricting by two atoms, is the same as restricting by 0 atoms, whereas if I abstract by MA, and now I'm going to abstract by MB, and then abstract by MA, that's a different type. You see, we have two abstractions here. And I'll tell you now for free that abst MB in abst MA is going to be different, inherently different from swapping the two abstractions round. So we've forgotten the names, but we haven't forgotten the order. Whereas morally, res MA MB, res AB is morally equal to res BA. And although it's morally equal, you have to use unifiable perm to detect that. Good, Jane, thank you very much. Hands up if we're good to carry on. Perfect, thank you. And let's just do one more. So let's ask what the support of a set is. And thank you for the smiley faces. Keep those emojis coming. It's all helpful feedback. Oh, did you question?
Yes, please. Is support total? Is the support function total?
Yes, it is. What would not be total about it?
I'm thinking they might have a function that generates names on the fly, but I guess what you're telling me is that it's about the names that appear in the definition of that function. Is that correct?
Hang on one second. Let's try. I'm not sure I fully understand your question, but let's ask what the support of this function is. Okay, we're going to get a type error because there's no instance defined on functions. And this is related to functions. They're not an equality type. Haskell doesn't let us go into a function to check what names might be in it. So what support does is, the mathematical support is confusingly different from the Haskell support. The notion of support implemented in this data types package is purely structural. It has a few type formers that it knows how to go through, basically tuples, lists, and sets, and it just collects any atoms it finds. Yeah, cool. Good question. Thank you. So I'll just try this now with S from list AB, and I reckon that should give us the set AB, which is fine. And now I'll try to get fancy, and I'll restrict A in this set. Oh, sorry. There we are. Now, the reason I mention sets is because unified perm doesn't know how to deal with sets. So the unified perm machine is very similar to the support machine. The only difference is that support knows what to do with sets and unified perm doesn't. It's not terribly important, but for those of you who recall, I didn't tell unified perm how to deal with sets because it leads to a factorial explosion in the search space, which I just didn't want to get involved in. So it's not a mathematical reason, it's purely algorithmic. SUP has no such problem. It's perfectly happy calculating the support of a set. The support of a set is just the union of the supports of its elements. So if I do this, there, bam. Yes, Mateusz, question.
So what if I restrict on another restriction? So
Let's
I do
it
twice, like you did with
res A, res B, like this, for example. Yeah?
Yeah.
So that's what it does in the support. Let's look at what this thing actually is. Res A, res B in the list ABC. Let's look at the type. I think I know where you're coming with it, coming from with this. You're saying, well, hang on, here we have the restrictions have accumulated, just like the abstractions. Is that what you're getting at, Mateusz?
Right.
Yeah, that's fine. So what you are discovering now is the restrict function. There we are. You can see
and
that
now they collapsed.
Yeah, exactly. But really, I mean, this is an advanced answer, which I'm going to give you in a moment. For now, I'll just point out that unlike abstraction, restriction is monadic, so I can hit it with join. What have I missed? Oh, sorry, I'm having a stupid attack. How do you flatten down a pair of monads? What's the command?
Add control monad to your context. It's the easiest solution.
Oh, I see. Thank you very much. Many thanks. There. Okay, so Mateusz has noted that the type of res is from A to nom A. So if we do two reses, we get two noms. And my initial answer to that is that's fine because nom is a monad. If you apply two abstractions, there's no native way to smash them down to a single abstraction because abs is not monadic. Does that make sense?
Absolutely, yes.
Thank you. In a sense, that's smoke and mirrors because abstraction by a list of atoms is naturally monadic, but the counter-argument, just by concatenating the lists, but the counter-argument to that is, oh no, still, you have to remember the order and you have to remember any vacuous bindings. So this is something I just haven't got round to building in the current system, which is abstraction by a list of atoms. There's absolutely nothing wrong with that. I just haven't done it yet. But there's something deeper going on, which will be revealed when I talk about restrict, which is on the list. Did someone else have a question? Okay, I will carry on. So that's it for support. Oh, restriction. Haha, Mateusz, you're ahead of the curve. So let's talk about restriction. This is an interesting function. So let's look at this. Restrict is a function which, assuming that A belongs to the type class restrict, will take a list of atoms and restrict those atoms A in A. So let's ask what types have a restriction action. So let's ask restrict A in AB. Oh, and I'll tell you for free. Now, ladies and gentlemen, those of you who are half asleep, try to wake up because weird things are about to happen. The intuition of restrict A in X is please remove A from the support. Yes, so that's why I did support first, because I need the idea of support in your head so you can understand what restrict is trying to do. So the intuition of restrict is restrict AX equals please remove A from the support of X. Okay, so restrict A in, let's try restrict A in AB. So restrict the atom A in the list AB. How could we remove, let's just check the support of this thing. Yeah, so the list AB has support AB. Have I? No, I didn't press, oh. No, I don't think I did. Yeah, it's still there because it was full of syntax errors. Swaresh, thank you for the looking out for me. There. Can anyone suggest what this might be? Okay, guys, focus, please. What do you think this should return? Can I have a volunteer, please? Nathan, go for it. Nathan, you have to unmute yourself.
Whoops. I'm always going to forget that. I guess C comma B if it weren't redefined, but I'm 99% sure it's redefined.
Restrict is not redefined. Don't worry.
Okay.
So you
then a fresh var comma B maybe?
Oh my God, it is redefined. You're right. Look at the type. Oh, I'm a complete idiot. Oy vey. Okay, guys, I apologize. You're right and I'm wrong. So what am I going to do? I'm going to have to reload my environment, aren't I? Bugger. Okay.
Maybe just re-import nameset. It'll work.
Okay, import.
Oh, unfortunate.
Hang on, I'll try. I don't actually remember where restrict was defined, so I'll just. No, I'm going to have to exit, re-enter, but that's okay. Apologies for all of that. My mistake. Oh, somebody has suggested undef. I'm sorry I missed that. I could have learnt something interesting there. What have I? Oh, lost. Well, I could have done without the interruption, but there you are. Okay. And now I just need to input these. Guy, thank you very much for your suggestions on how to fix that without doing what I'm doing now. I should have stopped to listen. So I appreciate the support. Here we are. Okay, so let's try again. So restrict. Excellent. Okay, so restrict A in A B. So Nathan, what did you think? You thought it should be something like CB. Is that right?
Yeah, or a fresh variable B.
Sure. Okay, so just check out the type. If we look at the types here, this corresponds to this, and this is atom list, which corresponds to this. So we need an atom list. So how are we going to remove A from the support of this atom list to get another list of atoms? Okay, I'll carry on. Nathan, thank you. You ready? Let's find out. So that's given us B, hasn't it? Does that make sense, Nathan?
How would this work on like a tuple, I guess? Would be my
Let's try it. That's a great question. Let's try it. So Nathan is asking, how are we going to remove A from the support of a tuple AB? We don't. So tuples don't have a restriction instance. Well, actually, no, it's more subtle than that. Check this out. You ready for this? Nathan, you can, yeah, okay, here we go. Oh, I don't have it. That surprises me. It looks like I forgot to tell restrict. No, I must have told restriction to go down through tuples. Evidently not. Okay, I apologize. So I'll just change it to this. You ready? There you are. So we see what restriction is doing on this. I will make a note to myself to switch restriction on for tuples. You can mute your microphone now, Nathan. Thank you.
Or I guess I actually have a question about what that just returned. Could I ask that quick?
Yes, of course, please.
Why is it not empty list, comma, list containing B?
Very good question. So the machine for lists specifically acts as a filter. So when restrict encounters a list, it removes any elements from the list that have, in this case, A in their support. Now there's a design choice here. Let me illustrate it with the next example here, and you'll see what's going on. Okay. Now you see here there are two things that restrict could plausibly do. It could return nothing, which would be like with lists. It could recognize that A is in the support of just singleton A and return nothing. Agreed? Nathan, agreed?
Yeah.
Yeah. Or it could go underneath the just and just try to restrict in the list, in which case it would just remove A from the list and return the empty list. The question is, which is it going to do? I can't stand the suspense, I'll just press enter. And we see here that restrict goes down through maybe, but it acts as a filter on lists. Nathan, please unmute your microphone. Thank you very much. Grino, you had a question? Okay, please ask your question. Oh, you'd like to type it. Okay. Well, you type, I'll keep talking while you're typing. Swaraj has asked, what should we, Swaraj has asked, what should we have gotten? Yeah, if Jamie had not forgotten about this. So the obvious thing to do with a tuple is to act pointwise. So restrict would go down and return, just as you said. I'll just type it out. This is what I would expect to see. I just forgot to program the machine to do it. Okay, and Grino has asked, would it make sense to type restrict A in A? Great question. So restrict is trying to remove A from the support of A and return an atom. I say there's no sensible way to do that. So this should definitely return a type error. Restrict atoms should not be a restriction type. So there's two functions which confusingly have very similar names, but they're quite different. There you are. See, and the difference is res takes an A and returns nom A, whereas restrict assumes that A already knows how to remove A's from support and just triggers the remove A from my support action on that type. And Grino has had a light bulb moment. Any questions on this before I continue? Okay, hands up if I can carry on. Perfect, thank you. So how about restrict A in 1? Alexander, yes, you had a, okay. Well, what should this return? Now, let's think it through. 1 is nameless, it doesn't have any atoms. So to remove A from the support of 1, we can just return 1. Let's try that. There. Okay. And let's try something else. Let's try to return A from Ah, I see. Right, so just to be clear, this A here is a char is nameless, so we don't touch strings. And importantly, one second please, importantly, truth values are also nameless. Sorry, I meant false. Okay, now this matters. I'm going to show you applications of this in a minute, but Guillaume has asked, does it make sense if restrict returns just A? What is the argument to restrict here? Is this restrict A in A? Are you suggesting that should return just A? Guillaume, I've asked you a question. Okay, no answer. So let's just look at the thing which returns a type error. Recall that the type of restrict is A to A. Well, the type of restrict A is A to A. So restrict, this cannot return just A, but restrict A and just A could plausibly return nothing, but it doesn't. So when I designed this, I had two major choices, how to deal with maybe and how to deal with lists. And I looked at the programs I wanted to write, and on balance, I chose to set maybe to just go through. So restrict goes under a maybe and looks for a restriction action on the interior type, whereas list acts as filter. This could be confusing where you've got, well, I'll just show you. Restrict A in just singleton A. This could plausibly return both just empty list or nothing, and it returns just empty list, whereas if I swap them round, this could plausibly return list of nothing or empty list, and it returns empty list. Hands up if you're if I can continue. Thank you. Hands down. Oh golly, now's a good time for a break. Okay, I'll take. Let's take 5 minutes and then carry on. Okay, I will just get straight to it if that's all right with you. Hands up if I can just continue, please. Thank you. So we've discussed restriction, and now let's talk about unnorm. There's a family of 3 functions. Just so you have an idea of where I'm headed, this is where I want to get to. This stuff here. This is where the action is, but I have to explain unnorm and new first. So let's look at unnorm. This says if A has a restriction action, then we can map from nom A to A. And it's obvious how this is going to work. We will expand the nom with some names for the restricted atoms and then restrict them in A. So this is a folding down operation. It folds down this, if you like, restriction that lives at the type level down into the into A using A's restriction action. Maybe best explained with an example. So if I restrict A in res empty list A, I'll make it say AB. So here we have something that is a restriction, a trivial restriction over AB, but crucially, nom has its own restriction action given by adding atoms to this restriction environment. So I'd expect this A to go into here. I will demonstrate. What did I do wrong? Oh, well, you know what? I'll just use. Oh, I see. Right. So this is quite an interesting warning here. The type checker doesn't know that this is a restriction by atoms because we have multiple types of atoms. So I'll just put in a dummy C. That should work. There you are. So now we see that. I'll just check the number of A. Yeah. This here corresponds to A, and we see that it's got bound, and this 4 corresponds to C. Hands up if you're okay with that. Thank you. Perfect. So check this out. I'm going to restrict AB in the list ABC, and now I'm going to unnom it. So what's this going to do? Well, unnom will check whether this list type has a restriction action, which it does given by filter, and then it will, well, it will basically rewrite into restrict AB in ABC. Maybe that's a good way of wording it. So unnom, in this case, on a nom type, folds this restriction into an actual restriction on the underlying type. So I would expect this to return singleton C, which it does. However, unnom on other types will do other things. So, for example, if we restrict A and B in just, I don't know, res C ABC, here, let's just work through this. So, no, I want this. Here, I would expect unnom, it will ask maybe, what's your restriction action? And maybe we'll say, I don't know, look at my underlying type, which is a nom type. So unnom will now trigger a restriction action here. So I would expect to get, sorry, I'll give myself another one. I would expect this to act as a join in this case. Have I done wrong? Oh, unnom needs a, my mistake. Sorry, that's restrict I was doing. Oh, indeed, thank you. Maybe that's it. But also, unnom needs a nom. So I was basically just being stupid there. See if this works. That's what I was thinking of. Never mind. I'll just work through the examples. It's safer. So let's do this. There. So that's the example I gave before, whereas this one here, this is the example I was trying to recreate. So this should act as a join because the restriction action on here is given by it being nom. Bang. So can you see this A and B have been folded down into a single restriction environment? And I'll try one more, which is I'll try to unnom. So this thing has type nom bool. And the restriction action on bool is just to throw away the binder. So I expect this to return false because A is not equal to B. So unnom is quite versatile. Given any nom type, so long as this type knows how to restrict atoms, it allows you to escape. So this is a really useful way of escaping from a non-binding. Hands up if I can carry on to new, please. Thank you. So in some sense, the examples I've shown you for the past 3.5 hours have been slightly artificial. This is what programming in the nominal data types package really looks like much of the time. In fact, you have a bunch of stuff with nom floating around on it representing local bindings, and at some point you arrive at a type where you're happy and you want an output, and then you can use unnom to escape. Well, this is another way of using the package, shall we say. If you look at system F, you'll see the kind of declarative names a data kind of thing. Now I'm showing you how to manipulate local scopes. This is a local scope, and unnom says if your underlying type has a restriction action, has its own notion of scope, then you can fold the local scope down into the type. Now let's look at new. New is familiar from nominal techniques. This is the new quantifier. It uses names, so you need to provide a label. So for a new unit labeled name, MD equals MA, that should return false because MA is in scope. If we generate a new atomic ID, label it with unit, and then check whether this new ID is equal to MA, it should return false. Perfect. There's new A, which just works with atoms instead of names. So new A, so is a, we take a fresh atom and return the length of singleton D. So this, I think, should return 1. Did I do wrong? Oh, yes, no, this is deliberate. This was not an accident. I had planted this as an example. So have I got, I'll just set X scoped type variables. So recall there's multiple possible types, like species of atom. So the problem here was, even though it doesn't actually matter, the type checker didn't know what kind of atom D I wanted. So I will tell it here. Now it returns 1. Any questions so far? Hands up if I can carry on. Good. Okay, thank you. So here's another one. So we create a fresh name labeled with hello world, and then we return the label of that fresh name, thus destroying the fresh atomic identifier that we just created. And sure enough, we get hello world. And finally, what does this one do? I don't even remember. So let's read it. We create a fresh atom D, and then we check whether D is a member of the support of restrict D in ABCD. Well, why not? So I reckon that D is not in the support of restrict D in ABCD because support works by filtering out this atom D. So I reckon this should return false. So here's a question. If I just delete this, what should this now return? I need a volunteer to tell me what this should return, please. Haha. Okay, so yep, that's right. So trick question. Now, what's the? Don't worry about it, Swaraj. Don't worry at all. Let's somebody remind me. How do you check elementhood on lists? What is it, please? What's the command? LM. So let's try that. And this should return true. In fact, I have a sneaking suspicion it might still complain. Oh no, it's fine. So there we are. Okay. Can somebody please think of a question before I continue? I need a question, please. When does new A return the opposite of expect? I don't understand the question. Can you be a bit more precise? Unmute your microphone and speak to me, please, if you can. Okay, he can't. So Guillaume has asked, when does... So are there any examples of when you work strangely? Actually, no, not really. I know it's partly my style. I'm quite anxious to emphasize all of the corner cases in my package, but don't get me wrong, not everything in this package is a corner case. Most of the time, it does do what you expect. Yes, Martin, you have a question.
How does you figure out which name to use, which atom to use?
It just uses fresh atom IO, basically. one of them. So what NewA does is it calls an IO action, generates a fresh atom, and then runs this. But this is all happening inside the IO monad. So hidden inside here, when I press enter, we move to the next step in the interactive prompt. That's a new IO action, and that's where the new D comes from. Does that answer your question, Martin?
Yes, I was just surprised that it doesn't show up in the type of NewA.
Right, now that's a really good question. So Martin has, let's look at the type of NewA. Martin has asked, how come IO doesn't show up in the type here? Well, that's because we assume that there's a restriction. So what happens is, NewA is given this function, it generates a fresh atom, but then immediately restricts it in the result of B. Now in this case, right, so just to say that in another way, it does show up in the type, it shows up here. We assume that the type B knows what to do with any fresh atoms that we might give it. Does that make sense, Martin?
Yes, kind of.
Kind of. Okay, so it might be simpler to look at this instance here. Here, NewA specifically has type K-atom to, it has type atom to bool, arrow bool. Now, bool is a special type because it's nameless, and its restriction action is to do nothing because true and false contain no names. So the reason that you don't see any fresh names appearing here is because whatever truth value I calculate, Martin, it doesn't matter what name I use to generate it. Does that make sense, Martin?
Yes.
Thank you. And this is actually a genuinely confusing point. Restriction is more powerful than you realize. It has a kind of dual role. Sometimes it's structural, like the natural restriction action on nom. The natural restriction action here is to add to the binding. But the natural restriction action on bool is just to throw away the atom. So restrict has a flavor of being like the new quantifier from nominal techniques. It's actually a very powerful assumption here. And it's used in two ways, either structurally like this, or when you have some final result that is nameless, and then you can, because it's nameless, you can use restrict to throw away any intermediate state that was used in the calculation. It's an important point of nominal techniques. You very often find yourself calculating with atoms to arrive at a nameless result, and these functions here, unnom and NewA, are how you escape from the local binding of names that you know don't matter anymore to return a result to the outside world. Hands up if I can carry on. Good. Thank you very much for your questions. Please keep the questions coming. Okay, now for binder. Now, binder is seriously non-trivial. This is arguably the most sophisticated type class in the whole theory. So binder has a constructor and a destructor. The constructor takes a, sorry, this is the constructor. The constructor takes a context and a body and returns the context with the body. And the intuition of this thing here is some kind of abstraction in its most general sense. You're supposed to abstract any of the atoms in the context in the body and return them as a nameless pair. So I have two examples here which I will type out. So check this out. Oh yes, and there are two instances of binder currently visible. One is abstraction, one is nom. So I'm taking this list and I'm going to try to bind it in MA. And I have to now guide the type system. I'm going to tell it I want to return a nominal abstraction. And bang, the machine goes into Binder, looks up the instance, and turns this into res AMA. On the other hand, if I take MA and bind it in MA, and I tell the machine that I want an abstraction, then it will return an abstraction. It does that, right? So what we have here in Binder is a general theory of Binder-like things, and these turn up all over the place. We only see two examples here. They're very important ones, but anything that binds can be made into a binder. Nom is the canonical binder, and is actually a function, binder to nom, that will turn any binder into a nominal restriction, a nominal binding of the context and the body. And conversely, there's a function nom2binder, which will convert any nominal binding into a specific binder. So nom is there's a canonical representation of any binder as a nom, but usually, often it's useful to work with a binder directly, as for example with abs. I think there's a function abs to nom, which will take an abstraction. So abs to nom is literally just binder to nom instantiated to abstraction. Abs to nom of abs ma returns restrict a in the pair ma. I can probably go the other way round as well. Nom to abs. Nom to abs, sorry. Yeah, that worked. So that gets us our abstraction back again. That was quite a heavy dose. Any questions? Hands up if I can carry on. Okay, I'll take you at your word. And then we have the destructor. And actually 3 destructors. I'm going to show them to you now. So this takes a binder and a function that takes a context and a body and returns a B. And another name for this is, what do I call it? GenApp. I call it GenApp. This is a really bad name. I have to improve on it, but that's what it's called right now. And then there's this, which take a context and a function that, if we think of this as a context binding some names in a body, then this is a function that takes the context and the body and returns a B. Now, when we break this up as a context and a body, we might need to generate some fresh names because the names in the context are bound in the body. And then those names just get slapped onto a nominal restriction at top level. Let's see if I can create one now. So I'll give myself an abstraction, and then I will try to unpack it as I'll take the context and the body, and I'll just map it to the pair of the context and the body, right? And bang, what do I get? I get this corresponds to that, this corresponds to that, and this corresponds to the fact that A is bound in this. Hands up if that makes sense, please. Okay, that's good, thank you. Does anyone have any questions? Okay, let's try this with the exclamation mark. Exclamation mark is intended to suggest some kind of forcing. So, well, I'll just show you what happens. This just gives us a pair of, it's not MAMA, because we've generated a fresh name for the bound atom here. So this is a generative version that just doesn't safely bind. So this is unsafe for a particular notion of unsafe, whereas this is safe. I'll just take a slightly more complicated example. MB, there we go. So there we can see the MB living in here, and we have generated a fresh name here, right? Blah, blah, blah. And if I do this here, then the name is bound here. Okay. And finally, let's try it with dot. Now I should show you the type at dot. So the crucial thing about at dot is here with the restriction here. Now, if I left you the type about this, you'd figure this out. What we have to do is to use this restriction action to restrict any of the atoms that were bound by the context in the body. So we generate these fresh atoms, we calculate our B here, and then we will apply a restriction on the B to rebind any atoms that we created when we applied this function. Hands up if that makes sense, please. Okay. Oh, Had, you didn't put your hand up. Do you have a question?
I did, but I put it down very quickly after that. I did understand.
Okay, thank you, thank you. So I'm going to, if I do this, I'll get a type error just because tuples don't have a native notion of restriction. But if I make this into a list, which is kind of a stupid example, but let's see what happens. Oh, what did I do wrong? I can't be bothered with. So I'm just going to restrict MC here. Oh, hang on. Sorry, there. What did I do wrong here? It's something to do with what, yeah, okay, so the problem here is this doesn't know, it hasn't figured out what atom context name. Thank you very much, thank you. So I'll just do this, this will give me a type error. Yeah, okay, so maybe this will work. Thanks for that, guys. Yeah, and that returns the empty list. Why? Well, let's just look at what the intermediate state that's generated. This is atom 53, atom 53. When I put this dot here, the system tries to restrict atom 53 in the result, and in this case, that filters. So, bang. I'm seeing people doing time warnings. Am I running out of time? Okay, I'll carry on. Okay, so this is just what I've done. Okay, so in the last 15 minutes, I'll just carry on. So if you actually look at the files, you will see this is the major way that we interact with the name binding operators, right? This is, as I said, there are two styles of programming. There's one where you just treat names as data, you generate them freely and throw them around any way you like. There's another style where stuff is held under local norm environments, and if not a norm, then some kind of binder. That's important. You're not restricted, pun intended, to using norm. You can declare your own types of binders and use them, and then this little trio of functions is how you escape in various ways. This escapes to a norm. This escapes, quote, unsafely by generating atoms, but if you do it at the right types, that's not going to matter. And this escapes by folding any local names into a restriction on the type. Hands up if that makes sense, please. Thank you. Okay, now actually we have a choice. One thing we can do is we can look at some code. The other is we can go through some comments on style and concretion. Who wants to look at the code? Who wants to look at the comments? Thank you. Who wants to look at the comments on style and concretion? Here we are. Okay, could you just fill in fill in this poll, please? Grino, did you have a question? Okay, so I will continue with concretion and style, and then I will stop. So you may recall, thank you very much for answering, you may recall that we have a concretion action on abstractions, but actually concretion is more general than I let on. So let's consider restrict A in AB, which is fine, and I'm going to concrete this at unit. What could this possibly do? Well, this folds the restriction down into the type. This is our familiar filtering, right? So I'll give you another example. Perhaps you'll see how this works. Res A, res B in AB, and I will concrete this thing at unit. So concretion at unit type, it's just a little Easter egg I put in, triggers a restriction operation. Hands up if you're okay with that. That's good, thank you. Let's try something else. We restrict A in AB, and I'm going to concrete this at singleton A. What could this do? This triggers an unsafe generation. It basically, the system will try to identify this name here with this name here. So if I send this to C instead, you see there, this is AB, this is CB. But I can do much worse. I can restrict AB and AB and concrete it at BA, and that returns me BA. If I do that, we're fine. If I restrict it at B, it gives me that. So this is, I've actually never used this in anger, but I thought it was quite nice, so I put it in. We'll see if I come to regret it. I'm smiling. Now let's talk about style. The package is deliberately permissive about what it lets you do. So I've written a function bad count binding. This takes a nominal binding and returns an integer, which is, what do? Well, we take x primed, which has type nom, we unpack it as a list of atoms and a body, and we return the length of the atoms, the length of the binding. So let's try bad count binding in res A, AB. This should return 1. But if I do res ACAB, it should return 2. This is kind of impolite. You're not supposed to peek at the bindings directly here. C is vacuously restricted, so we expect res AC to be equal, I have to say unifiable. This is unifiable with res A AC. This should return AB. This should return true. Yeah, so we really shouldn't be doing this, but the system does let you do it, and we can, frankly, we can do much worse. We can do really bad, where we actually just return the atoms itself. Really bad count binding applied to res AC AB. Whoops. Returns a pair of fresh atoms, is that right? Yeah, a pair of fresh atoms, which is these two atoms here. So this is a really, really impolite thing to do, but the system allows you to do it. It has to, because we don't know what you're going to do with these atoms. So this could be embedded in a larger program that uses this local binding of atoms in some way that we know is safe for other reasons. The system doesn't try to stop you from doing these things, but if you do write a program like this, you should think, do I really know what I'm doing? Now, here's a different kind of bad style. this is the restriction function. This is how it's actually implemented. So if we want to restrict an atom in nom, we basically do it monadically. So this is good. Hands up if you want me to run good restrict on an example. Hands up if I can carry on. Okay, I'll take the carry-ons to win this one. Here's a bad restriction though. It actually works fine. It's not bad because it doesn't work. It does work. So let's look at bad restrict. If you run this program, it'll work fine, but it's in very poor taste because what we're doing here is we're trying to restrict these atoms in A primed, and we're doing it by unpacking A primed as a list of fresh atoms in A, and then we re-restrict those fresh atoms and these atoms primed that we're adding. Do you remember I said before that really bad count binding was it was allowing the atoms to escape? So here we see that there's an intermediate state here where we have generated fresh atoms for the bound atoms in A primed, and actually that's perfectly safe because we immediately restrict them again, but if only computationally, it's in bad taste because we're forcing a generation of a bunch of atoms which then immediately get restricted. This is clearly the superior program. Hands up if you're okay with that, please. Thank you. Okay, and then one more example. I just want to show you a bad implementation of equality. This is how equality is actually implemented in the file. So there's an unnom here, but this unnom is living at a bool type. Bool is a nameless type, so this unnom is completely safe. All it does is throw away any locally generated names, and we know we can do that because we either have true or false, so it really doesn't matter what names we used here and here. So this is a good way to calculate equality. This is a bad way. We take A1 primed and we unpack it as a body. Then we take A2 primed and we separately unpack it as a body, and then we check whether A1 is equal to A2. Now that looks all right, and it works, but it's in bad taste because we're doing the generation in 2 steps, and we really shouldn't. We don't have to. We should leave the generation of the names to the final stage when we have our computation set up, and then we run it and throw away the freshly generated names. So this happens in 1 step, so it's inherently safer than this 2-step generation here. Okay? Okay, any questions on that? Hands up if I can carry on. Okay, ladies and gentlemen, it is 11:53 and I am absolutely knackered, so I'm going to stop talking and thank you very much indeed. This is an absolute marathon and I'm amazed by your stamina. You've done this twice in the week. Ohad, over to you.